All right, in chapter 8, what we're going to do is we're going to extend what we've talked about with trig to deal with triangles that are not right triangles. The only triangles we've seen so far are in the context of SOHCAHTOA, where we've needed it to be a right triangle. But really, what we want to be able to do with trig is to be able to make inferences about any triangle, whether they have a right angle or not. And that's what we get into in chapter 8. The first way we'll be able to talk about these non-right triangles is using this thing called the law of sines. And the law of sines comes from kind of an interesting place. It comes from a formula that deals with the area of a triangle, which is something we haven't seen at all. So a couple things. First off, when we talk about arbitrary triangles in this chapter, what we'll do is we'll assume that these triangles have three angles, and they'll be capital A, capital B, and capital C. And then we'll assume that the side lengths are little a, little b, and little c. And little a will always be across from capital A, little b will always be across from capital B, and little c will always be across from capital C. And in this picture that I drew, it looks like I have an acute triangle. All of the angles are less than 90 degrees, but we're not even going to assume that. We're not going to assume that this is drawn to scale or anything. All we know is we have a triangle, and it's got these three angles, and it's got these three sides. And the sides are always opposite where the angles are. So what I want to do is I want to come up with a formula that tells me the area of this triangle. And you're like, whoa, I'm way ahead of you. I already know a formula. The area of a triangle is 1/2 the base times the height. Maybe you learned this back in a geometry class. You took two triangles and put them together and made a parallelogram and then cut those up and turned them into a rectangle. And you're like, I know the area of a rectangle is the base times the height. And since I took two of these triangles to make this thing, the area of each triangle must be 1/2 of that base times height. Remember that? Maybe, maybe not. Doesn't matter. The point is you probably have this formula memorized for the area of a triangle. It's 1/2 the base times the height. So what if I wanted to know the area of this triangle over here? Well, there's a problem. I know the base. I could use this little a as the base, for example, but I don't know the height. B and C refer to the side lengths from here to here and here to here, neither of which is the height of this triangle. The height of this triangle would be the length of a line that connects the base to one of the edges and forms a perpendicular angle at the base. In my arbitrary triangle, I could label that height with the letter H and make this picture. The problem is, remember, in these triangles, all we know are capital A, B, and C, and little a, b, and c. We don't know H. However, we saw something kind of like this earlier in one of the proofs that I did. We can come up with H in terms of these different side lengths. The fact that the height forms a perpendicular with the base creates right triangles. Right? I got a right triangle right here on the left side, for example. There's also one over on the right, but I'm going to use the one on the left just because. Note that in this green triangle here, I don't know a whole lot of information. I don't know this side length over here. I don't know the height. I do know this side length B, that's nice. I don't know this angle up here. I do know this angle, it's 90 degrees, and I do know this angle, it's a capital C. So using what I do know, I want to come up with an expression for H. Well, let's see, I know B. If I want to relate together H and B, and I don't have this angle up here, but I do have this angle, relative to this angle, height is opposite and B is hypotenuse. So I could say that the sine of capital C would be equal to H over B. That's just SOHCAHTOA. Sine is opposite over hypotenuse. So I can solve this equation for H by multiplying both sides by B and get that H is B times the sine of C. I now have everything that I need to figure out the area of the triangle in red. The area of the triangle in red is 1/2 the base. The base is A here, times the height, which I just solved for. It's B times the sine of C. What I'm saying is instead of thinking about the area of a triangle as 1/2 the base times the height, you could think about the area of a triangle as 1/2 AB sine C. This new formula can be better than the old formula in the case that you don't already know the height. If you just know the three side lengths and the three angles, which is where we'll be in this chapter, it's really nice to have this formula to figure out the area. So for example, suppose we were asked to find the area of this triangle. We know that this side length is 3 and this side length is 4, and this angle here is 120 degrees. Fine. It might seem like we don't have enough information to figure out the area of this triangle, but we actually have exactly what we need. If we call this angle C right here, then this would be side length C. So we don't know little c, but if this is little c, then these are A and B respectively. So little a, maybe we call 3, and little b, maybe we call 4. We now have little a, little b, and capital C, which are all the ingredients that we need to come up with the area. The area is just equal to 1/2 times 3 times 4 times whatever the sine of 120 degrees is equal to. Well, let's see, 1/2 times 4 is 2, 2 times 3 is 6, so I get 6 times the sine of 120 degrees. The sine of 120 degrees, you might need to refer back to your unit circle, but I think what you'll see is it's the square root of 3 over 2. So 6 times the square root of 3 over 2, the 6 and the 2 make a 3, so I get 3 root 3 as the area of this triangle. The takeaway here is if we're lucky enough to know two different side lengths in a triangle and the measure of the included angle, So that's a term we haven't used yet, but it kind of makes sense. The included angle is the angle that touches both of those side lengths, so 120 degrees in this case. If you know two side lengths in the included angle, you can always use this formula to figure out the area. And you might be like, all right, that's great. I have a new way to figure out the area of a triangle. But is that really all that important? I mean, we haven't needed to know the area of a triangle this entire term. Is it important all of a sudden? Turns out no. Finding the area of a triangle itself is not that useful in the class, but being able to find the area of a triangle like this is going to lead to one of the most important formulas for this class. What am I talking about? Okay, remember this triangle that we had right here, where we had little a, little b, little c, capital A, capital B, capital C. I chose this little a to be the base here. But there's no reason I couldn't rotate this triangle a little bit and choose this little b to be the base if I felt like it, or choose this little c to be the base. I can rotate this triangle just fine. I would just have a different height. If c were the base, my height would look something like this pictured in blue. And if little b were the base, my height would look something like this. And you're like, yeah, whatever, I don't care. All you're doing is creating a really ugly picture. Okay, but the point is, if I choose a different base and a different height, my formula here will look a little bit different. I'm not going to actually derive it for you. I think it's pretty straightforward. You could do it if you wanted. But if I chose little b to be the base instead of little a to be the base, I could come up with a formula for the area where it was 1/2, and then instead of AB sine C, it would be BC sine A. And instead of choosing little b as the base or little a as the base, if I chose little c as the base, I come up with a formula where instead of being 1/2 AB sine C or 1/2 BC sine A, it would be 1/2 AC sine B. And you're like, yeah, great, whatever. You got three different formulas. Okay, the point is it's the same triangle. And that's really important. It's the same triangle no matter which side I use as the base and no matter how I calculate the height. So what that means is the area calculated this way has to be the exact same as the area calculated this way, and it has to be the exact same as the area calculated this way. I don't really care about any one of these three expressions for the area, but I do really care that all three of them are the exact same. Because the fact that all three of them are the exact same will allow me to come up with this thing called the law of sines. This has to be the same as this, which has to be the same as this. This gives me this equation relating together side lengths and an angle of some arbitrary triangle. So in any arbitrary triangle ABC, AB sine C has to be the same as AC sine B, which has to be the same as BC sine A. I'm going to have a hard time remembering all that, like which letters go with it, which. I can make this a lot prettier for you. What I can do, instead of multiplying each of these things by 2 like I did in this step, I'm going to divide each of these three things by A times B times C. I have an equation, so as long as I do the same thing to each thing in this equation, it's staying equal. But a nice thing happens when I divide by A times B times C. This A and this B cancel, this A and this B cancel, and I'm left with just the sine of C divided by C. This A and C cancels with this A and C, and I'm left with just the sine of B over B. And this B and C and this B and C cancel, and I'm left with the sine of A over A. This is what's called the law of sines, and it's much more important than being able to figure out the area of any one of these triangles. The reason I talked about the area of the triangle is because the area of the triangle is how we came up with this equation in the first place. It's the same triangle, so the area has to be the same no matter how you represent it. But the fact that these are the same gives us this equation, which will be super useful. This relates together angles and side lengths in arbitrary triangles. They don't have to be right triangles. And as we'll see in the next couple of videos, this is one of the most important things to take out of this class.